Section 1.3, Acceptable Methods of Data Collection. So one way that you could collect data would be a census. That's collecting data from the entire population rather than taking a sample. And we don't do this very often, and so there are some disadvantages to that. So let's look at those first. So we'll kind of do this a little out of order here. Why don't we always take a census? And there's two main reasons. One of them is that it can be expensive. If you're going to go out and collect data from the entire population, that's asking a lot of people, or just spending a lot of time really looking at what could be a very large population. The other thing is, a lot of times people say time consuming, but I've heard before that time is money, so I'm going to say that time cost is still an expense. So the other thing that we worry about is that it could be destructive. And one of the examples we talked about back in section 1.1 was testing how long a light bulb lasts, and to do that you have to burn it out. So you would never want to do a census in a situation like that, because you would burn out all of your light bulbs and have nothing to sell. As soon as you made more, then you are back to a sample rather than a census. So it can be expensive or destructive. Also in destructive, you could think of dangerous too. Maybe they're testing a new medicine that they're not sure what the side effects are, so they wouldn't want to just give that to everybody right away. So that's some reasons why we won't take a census. So we'll take a sample instead, but what are the disadvantages of taking a sample instead? And we talked about this back in section 1.1 also. The answers will only be estimates of the population values. And this means there will be sampling error in the answers, which is why we talked about using the word about or approximately when we make estimates from a sample back in section 1.1. But that's important to know. So we'd like to get the right answers so we could take a census, but that's expensive or destructive, so instead we'll take a sample, but that means we're just making estimates and are going to have error. So our real goal is to try and figure out a way to take samples so that the error is minimized and that we can estimate and calculate how much error we should expect. So we're going to talk about those acceptable methods of data collection in this section, but I'm going to start off with an example of a bad sample. So let's look at a bad sample from the population of workers in the United States and Canada. And I'm going to say my bad sample is NBA players. A lot of times I'll ask my class, is that a valid sample? And they'll say no, but it really is a valid sample. All that it takes for a sample to be valid is that everything in the sample is part of the population. But whether it's a valid sample and whether or not it's a good sample are separate questions. So this sample is valid because all NBA players work in the United States and Canada, but it's a bad sample because it gives too much sampling error in its answers for some variables, right? So what are some variables that would be a bad sample for? The number one thing I think we should probably think about would be income. Because when you're looking at workers, you start to think, how much do they make? And NBA players make a lot of money. If they were our sample for workers in the United States and Canada, we'd state our conclusion from these people about these people. So we'd end up saying something like the average worker in the United States and Canada makes $4.7 million per year, which isn't very accurate, right? A lot of error in there. Another thing we might look at would be maybe height, though that's somewhat strange that we would be studying how tall people are in the workforce in the US and Canada, but if we did, we would get an answer like the average worker is 6'7" or something like that. And then maybe one of the worst variables we could look at with this sample would be gender, because there are no women players in the NBA, so we would end up saying 100% of the workers in the United States and Canada are male. Lots of error in that estimate. So the problem with these is we have a sample that's biased towards higher incomes, biased towards taller people, and biased towards males. And we want our samples to be representative rather than biased. So a representative sample is one that contains the relevant characteristics of the population in the same proportion or percentage as they exist in the population. So our sample has too many wealthy people in it, too many tall people. It's not that we don't want wealthy people and tall people in our sample, because there are wealthy and tall people in the United States and Canada. But if it's only like 1% of workers who make over $1 million, then we only want 1% of our sample to be over $1 million. You can think about the question real quick: what should our gender mix be in the sample if we wanted a representative sample? And a lot of times people will say it should be 50% male and 50% female, but that's not right either, because we want it to match the population, which maybe has slightly more men in it than women. So it's not thinking about like what would be fair, but what would be the right match with the population. So if the population is 55% male and 45% female, we'd want our sample to be the same way. All right, so let's look at an example to see how that works. 57.8% of the students at Chabot are female and 42.2% are male. If we wish to have a sample of size 50 where gender is properly represented, then how many male and female students would be in the sample? So again, it's not 225 of each. We're not just going to split our sample size in half and say make it half men, half women. We want it to match the population. And the population is 57.8% female. So we would want 57.8% of our sample to be female. So for the female students, we would take the sample size of 450 and we would multiply that by 0.578, moving the decimal over 2 spots to write our percentage in decimal form, and we plug that into the calculator to see how many female students we want in our sample. We do the same thing for the male students. We take the sample size of 450, we'd multiply it by the percentage of the population that is male, which is 42.2%, but we would change it to decimal form first. And then just bring in the calculator real quick, do those computations. 450 times 0.578 is 260.1, and then 450 times 0.422 is 189.9. It's a good idea to just add those two together real quick. So 260.1 plus 189.9, make sure we really get the 450 that we're supposed to. But the other thing that we need to do is think about rounding. You can't have a sample size that's a decimal. So when you talk about how many female students would you want in your sample, it has to be a whole number. So we can't really get exactly the 57.8% because we have to go with a whole number, but just round to whatever's closest. A 0.1, anything 4 or lower, we would go down. So we're going to round this to 260 female students. And then 189.9, because of this 9, 5 or larger, we'd round up. So we would say 190 male students. So this would be the breakdown in our sample to make it as representative as possible for gender. I say as representative as possible because that's not actually perfectly representative. It's not 57.8% female. If you do 260 divided by 450, you get 57.7777778% female. Now that's really close to what we wanted, but it's not exactly the same. But that's typical because you can't have a decimal sample size. If you have to round to make that work out, then that's what you would do. So ideally, we would go through a procedure like this all the time to make our samples representative, and we wouldn't just do it for gender, we'd do it for every variable that we thought was important. So it turns out, though, that people don't do this. So what are some of the reasons why it's hard to make sure you get a representative sample? Why don't you go through and do these sort of calculations every time for every variable? And there's a couple answers to that. One is sometimes we don't know what all the relevant characteristics are. So when you're going to estimate, let's say, the average income for people who work in the United States and Canada, is gender an important variable? You might think about that and say, well, it shouldn't be, right? Men and women should make the same amount if they do the same job at the same skill level. But studies show that's not necessarily true, that men tend to make a little bit more than women. So if that's true, then it would be important to represent gender properly. Is height important? People would tend to say no, but studies have also shown that taller people make a little bit more than shorter people. So some of these things might not seem relevant, but they can be. So that's one of the issues, is that we don't know what all the relevant characteristics are. But let's suppose we worked it out and we did figure out what every relevant characteristic was. Even for those characteristics that we know are relevant, we often don't have the census information that's needed to represent the characteristic properly. So if you think about this, why are we taking a sample? Because there's something about the population that we don't know and we're trying to estimate it. So one of the things we might not know is the gender mix or the height mix or all kinds of different things. So we want to represent every characteristic properly, but sometimes we don't know what all the relevant characteristics are, and even when we do, sometimes we don't know what the right percentage mix is. So we're kind of in a tough spot, so we need to work our way out of it. And it turns out the method we use to fix this is simple random sampling. It's a procedure for which each possible sample of a given size is equally likely to be the one chosen. This may seem like we're just giving up when we go to a random sample, but I'll show you soon that this really does work out pretty well for getting representative samples. But first, we just want to practice the idea of getting a random sample. So what I'd like you to do real quick is, in your head, quickly, pick a random number from 1 to 5 and write it down. Don't go on with this video until you've written down that number. All right, now that you've made your choice, I've got some bad news for you. You didn't do it randomly. Let me go ahead and show you something on the computer with some data that I've collected from past stat classes to show you that when we pick a number in our head, it doesn't really do what simple random sampling is supposed to do. Okay, so I just had you write down a random choice that I told you to pick a number from 1 to 5 in your head, and then I told you that I didn't think that you had really done it randomly. So maybe that seems like a mean thing to say since that's what I asked you to do, but I'm basing that on lots of past classes where I've asked them to do the same thing and I've seen how it turned out. So here's the fall 2016 survey where I asked several students to do that, and here's their random choice answers. Shame on a few of them, they didn't answer the question. And if I look at that, let's see, let's make a graph for that where we do, let's just do a dot plot. And our variable is random choice. And I'll just click compute and it'll draw the bar graph. And so what we see here is kind of the distribution of those answers. And this is super common for what I see in classes when I ask people to raise their hand and tell me what they wrote down. Most people choose 3 or 4, with 2 coming in third and with 1 and 5 being the least common options. Now if this had really been done randomly, all of these stacks should be about the same height. Maybe a little different because of random variation, but semester after semester it turns out this way, where most people pick 3 or 4 and 2 comes in third and 1 and 5 fall behind. So if it comes out that way every time and it doesn't have that kind of equal height that you'd expect from random, then we must not truly be giving every number an equal chance at being the one chosen. And so that's why we need to find a different method of choosing random numbers besides just selecting it in our head. So as we saw from the data collected from a past class, picking a number in your head is not a good method for randomly selecting items. So what is our method that we are going to use? Well, the visual we want to use is names from a hat. So the idea there being like a drawing or a raffle. So if you really wanted to get a random number from 1 to 5, you should take 5 little pieces of paper that are all the same size and write the numbers 1, 2, 3, 4, 5 on those pieces of paper, fold them in half, put them in a hat, shuffle them up, draw one out. That would give every number an equal shot. But that's not always practical. And sometimes we're trying to pick workers from the United States and Canada, then we need a really big hat, right? So what we do instead is we use random number generators. And we do need to be aware that the human brain does not produce random output. There's all kinds of things that have been done where they ask people to try and fake random output, and you can always test it and kind of show that it wasn't really random, just like we saw with the random integers from 1 to 5. So a random number generator is actually just something that's being done with a formula that would be predictable if you knew all the inputs into the formula, but when you don't know them, it seems random, and when you try and test it to see if it looks random, it generally would pass that test. So let me show you an example of how that works on the TI-84 calculator. Use the random integer on the TI-83 or 84 to create a random sample of size 17 from the integers from 1 to 50 and do the sampling without replacement. So what we're going to do is we're going to go through the math menu to the probability menu, and we're going to put random integer from 1 to 50, and that's going to get us numbers. So let me go ahead and show you how that works. So here's the math button right here, so I'm going to press that. There's the PRB right there, so use the arrows. You can arrow to the right or the left, kind of sneak around if you want. And then there's a random integer option down here. So I'm going to do that, random integer 1, 50, and I'm going to press enter, and that would be my first number, 27. And then there's a couple things, like you could do it again, right? So math, probability, random integer 1, 50, and press enter. But that's kind of a pain. If you hit second enter, it'll pull up your last calculation, so that's a lot faster. But it also turns out if you just press enter, it'll repeat your last calculation, so that's the fastest. So having done it once, I can now just press enter several times until I get my list. So every time I press enter, it's just executing that random integer 1 to 50 for me. And I'm just going to keep doing that, keep writing down the numbers. You might notice if you're doing this along with me that you're getting different numbers, and that's good because this is a list of random integers. And so if we were both getting the same list, that wouldn't seem very random. And I just noticed something, which is that I had a repeat. So I had a 9 here and then another 9 there. And it said to do the sampling without replacement. So we're supposed to be thinking there of this idea that we're drawing these pieces of paper out and that we drew the number 9 and we threw it away in the garbage, right? Without replacement. We didn't put it back. So there's no way you could choose 9 again. So when you're doing this sampling without replacement idea, if you get a repeat, what you need to do is just ignore it. And so the longer the list, the harder this can be, but you just need to kind of keep an eye out for repeats. So I did my best to catch repeats. The 9 was the only one I noticed. If there's something else I missed, sorry about that. That's just the toughness of the process, I guess. But that's what we're trying to do, is just keep going until we get 17 numbers with no repeats because it's sampling without replacement. The only way you could get repeats if you had 2 pieces of paper in there that said 9, that would be fine. But the way that we're setting this up, we're just giving every number one shot. All right. So again, what you want to do to make that work is choose math, probability, random integer, a, b. And in this case, 1, 50. One of the issues that comes up sometimes at the beginning of the semester is that people have not yet got their TI-83 or 84s, and yet in our first homework assignment, we do have some problems that ask us to do some random number selection like I did up above. So if you don't have your calculator yet, so if you don't have that TI-83 or 84, another suggestion would be for you to go to the website random.org, and they have a free random number generator there that you could use while you're doing your homework on this chapter 1 and while you're waiting for the calculator to come in. But what you should not do is just write on your homework, I don't have my calculator yet, because we've got an option right here without the calculator to get the work done. So before we move on to other acceptable sampling methods, let me go ahead and show you on the computer real quick how the random.org works, and then we'll move on. Alright, in this video I just wanted to show you how to use random.org to get some randomly selected numbers. So if you go into your browser and you type random.org in there, it'll take you to the website. They'll tell you how and why they're the most wonderful place ever to get random numbers. They have a little random number generator right here that you can just use instantly without reading their paragraph. And what we were trying to do was get 17 numbers from 1 to 50. So you can just change the max here to 50. And then click on generate, and it'll come up with a random number. Click again, you get your next one, and your next one, and so on. So we could just do the same thing we did with the TI. Keep clicking these and writing down our list. Remember that if you're doing the sampling without replacement, that you have to be on the watch for repeats and ignore those and keep going until you get 17 unique numbers. However, there's some other ways to do it besides just clicking this that can be a little faster. So if you go to this option up here for random numbers and choose integers, then you can just tell it right away, I want 17 random integers to be from 1 to 50, and it doesn't really matter how we lay that out, but let's say we'll do, say 10 columns. So if I click Get Numbers on that, that works pretty good, except we get repeats, right? So if you're going to do it with that, you probably would want to do something like maybe 22 numbers, and we'll just do 11 columns, so there's 2 per column. And then you'd get your numbers, and you could just start writing them down, 33, 41, 31, 23, 47, and 1, and so on. But when you get to a repeat like this 1, you would just have to ignore it. So we did some extra ones just so we could make sure we got to 17. And then the final option, which is the best one, is to do this integer sets option. If you do that, you just want to create one set that has 17 numbers in it that go from 1 to 50, and notice it says unique numbers, so that means we're not going to get any repeats. And then there's some options here that I don't like sort the members into ascending order. I would rather just see them the order they were selected in, so I'll deselect that option, click Get Sets, and then there's my 17 numbers, and there shouldn't be any repeats in there because, again, they're supposed to be unique. So you can just use your TI-8384, but if not, random.org is something you can use until then. So hopefully that is helpful for you, and just try and use this with various changes made to fit the homework problems that you're doing. Alright, this is just a quick video to defend the idea that when we want a representative sample, we're going to use the method of simple random sampling. That may sound kind of like we're giving up, but let me show you that it does work out pretty well to get a representative sample by choosing your participants randomly. So we did an example in the notes where it was a population that was 57.8% female, and then we wanted to take a random sample of size 450 from that, and the idea would be that our population is 57.8% female, so we want our sample to also be 57.8% female. So what I'm going to do is just randomly pick 450 people from the population. So on this, every time I click one trial, if it says success, that means we got the trait we were looking for, which in this case was female. And when it says failure, that means it wasn't, so we have a male. And then over here, it's tracking the percentage as a proportion or decimal. So it was at 100% at first because we got a couple women, and then when we got a male student in there, it dropped down to 66.7. So as we do this at first, we see that it's kind of all over the place. Okay, this blue line right here though is 57.8%, and notice that at the beginning, while we were way above it and way below that line at times, as time's going on and we're getting more and more people in our sample, we're getting closer and closer to that target line of 57.8%. Right now it's at 60. If I click automatic, it'll just run that out, and I'm going to pause it as it gets near the end here. And what you see is that all of the real big random variation where our sample wasn't very representative was at the beginning when our sample size was small. But as our sample size is growing, we're getting closer to that target line of 57.8%. Right now it's 58.4. So we're getting a decent representative sample just by choosing randomly. If I finish it up, it'll rescale this to 4,000 on the far end, and we ended up at 58.22%. Not that bad, not that far off from the target. If we do it again, we get something different, still that chaos at the beginning, but as our sample size increases, the random variation tends to decrease in this part of the graph, and we end up reasonably close. We're off by about 3% here, so that one's kind of bad in a way, but that's still pretty close. So given that we can't really go through the procedure of pinpointing exactly how many females to put in our sample because of the problems discussed in the notes, this is pretty good that we can do a random one, which may be really far off. Our sample size was small, but if we let it run, we're going to end up somewhere in the neighborhood of what we were trying to represent. So when we get a random sample, it's not really giving up. Continuing on with section 1.3. Okay, up above we were talking about simple random sampling and showed some ways of getting that with random number generators, and that method of simple random sampling is the one that we base the math on later in the book. So when we do those future problems, they'll usually start out stating that we began with a simple random sample. However, there are times where people go to other methods, and those methods can sometimes still be considered acceptable. So we want to look at the reasons why that happens and what the consequences are. Sometimes it makes our sample a little better, sometimes a little bit worse, though all of these are considered acceptable alternatives to simple random sampling. So let's jump in and have a look at that. So other acceptable sampling methods. Sometimes people use methods other than simple random sampling to choose their samples. Sometimes a simple random sample is too difficult to obtain, and sometimes the researcher is not willing to leave the representation of certain characteristics up to chance. So when we say that a simple random sample can be too difficult to obtain, that can sound a little bit like a complaint. I'd like to do it the right way, but it's just too hard. And sometimes that could be it, but there are times where legitimately it may be even impossible to get a simple random sample, and we'll look at that a little bit in our next few examples. And when you're in that situation, it shouldn't be surprising that maybe your sample you end up with is not quite as good as simple random sampling. And then there's other moments where we don't want to leave the representation of a characteristic up to chance. Our goal is a representative sample, so if we don't leave it up to chance, then we should be doing something that gives us a better than random chance at a representative sample, and we'll see those examples as well. So here's an example that I'd just like to have kind of floating in the background before we get into the alternative methods. Every few years, Chabot conducts a student satisfaction survey. They decided a simple random sample was not practical, as many busy students would be unlikely to volunteer to come in and spend 30 minutes filling out a lengthy survey form. Instead, they decided to choose whole classes of students and to ask the instructors of these classes to administer the survey to the entire class during class time. To attempt to ensure a good mixture of students from classes of various subjects, they chose classes that were equally spaced throughout the schedule of classes. So the idea there with two things, if they randomly chose students, simple random sample, they could contact them and ask them to come in and fill out the survey, but we can't make students do that, so it becomes a bit of a volunteer survey where people can say no, and people who have really busy schedules are maybe more likely to say no. People who have a complaint they want to get off their chest might be more willing to say yes and do the survey, so it can cause some biases. And then when we talk about equally spacing through the schedule of classes, what we mean there is that maybe we chose something like every 30th class in the schedule. And then if there were 120 math classes and we chose every 30th class, we'd end up with 4 of those. And let's say that in the history department there were 60 classes and we chose every 30th class in the schedule, then we'd get 2 of those. So just a reminder, a representative sample isn't about the same amount of everything, it's in the correct proportion. So if there are 4 times as many math classes as there are history classes, it would actually be good that we had that proportion. I think I said 4 times as many, twice as many I meant. So getting 4 math classes to 2 history classes is right if there's twice as many math classes as history. All right, so let's look at some of the alternative methods now, and we will refer back to this as we go through some of these discussions. So one alternative method is called systematic random sampling, and that's a method of choosing your sample so that the sampled items are equally spaced throughout the population. And there are different ways of creating this systematic, equally spaced process. I'm going to go through one here. Others will come up as you do homework. And the key thing to knowing that something has been done in a systematic way is noticing that there's an equal spacing throughout the population. I'm going to show you how to do that through counting, but that equal spacing can also be through time, every 2 minutes, something like that. So there's different ways to do it. So here's the process of a systematic random sampling when you're trying to sample through the items. So step 1, divide the population size by the sample size and round that down to a number that we'll call k, and that will be our spacing. And then step 2 is to randomly pick a number m between 1 and k. That'll be our starting point. We saw earlier we probably shouldn't do that in our head. We want some random method for that. And then step 3, select the members that are numbered M, M plus K, M plus 2K, and so on. So just looking at that in terms of the abstract steps, that can be a little hard to follow. So let's look at an example to see how that works. Suppose that we had a population with 43 items in it. Maybe those are people, bags of chips, who knows. But there's 43 of them, and suppose that we have an easy way to number them from 1 to 43. Then if we choose 8 numbers using a systematic method, that would represent doing a systematic sample of size 8 on this population with 43 things in it. So if we want to follow these steps to get that done, then step 1 is to divide the population size by the sample size and round that down to K. So we're choosing from 43 numbers, so that's our population size. We're choosing 8 numbers, so that's our sample size. And if you just do the division on that, you get 5.375. You can verify that on your own. And then the step says to round that down to K. So our K is always going to be an integer. So if we rounded 5.375 down, we'd get K equals 5. And according to that, that's going to be our spacing. So when we start choosing our numbers from 1 to 43, we're going to be choosing every 5th number. Step 2 is to figure out the starting point. And it says to pick a random integer between 1 and K. So in this case, that's going to be random integer between 1 and 5. And I'm going to go ahead and use the calculator to do that. And whatever I get from that, that's going to be my starting point. So let's bring in the calculator and see what happens there. So math, probability, random integer from 1 to 5. And who knows what we're going to get? We'll see. Turns out it was a 1 this time. Could have been a 5, 4s, 2s. Eventually anything could show up there. Haven't seen a 3 yet, I don't think. There's one. But whatever we get, that's our starting point. So this time it happened to be 1. I'm going to tell you that that doesn't make for the best example, but when you're doing your homework, if you get a 1, you should do a 1. On this one, I'm going to pretend that what I got on that first try was the 2. So that would be M, and that's going to be my starting point. Again, in reality, you're doing these problems. If it's a 1, use a 1. If it's a 5, use a 5. I just think for the purposes of an example, it turns out a little nicer if it's a number in between. So then the final step is to list your 8 numbers. Start off with whatever is the starting point, so 2, and then keep adding the spacing until you get 8 numbers. So 2 plus 5 is 7. Add 5 again, we get 12. Add 5 again, we get 17, 22, 27, 32, and 37. And that's 1, 2, 3, 4, 5, 6, 7, 8 numbers from 1 to 43 that have an equal spacing where they're all 5 numbers apart. So a few quick notes on this before we move on. If I add 5 again, I get 42, and that is still in the range, but they only ask for 8 numbers, so when I get to 8, I should stop. Some other little things that are worth mentioning is if your first number had been 5.875, there'd have been a temptation to round that up to 6, but the process says to round down. So typically when we round, we use our standard rule. Is this digit a 4 or lower, we'll round down to 5 in this case, or a 5 or higher, we'd round up to 6. But here the rule says always round down. So even if it was 5.875, we would still have gone with K equals 5 for our spacing. And the reason for that is if you round up, depending on what you get as your random starting point, you might get to 7 numbers and go for the 8th and you're above 43. But by rounding down, that's never going to happen. So that's why they have what may seem like a strange rule there to always round down regardless of what your spacing looks like in decimal form. All right, now that we've seen an example of how to choose a systematic random sample, I want to talk about the effects of that on how good of a representative sample we have. It turns out that this method usually produces an advantage. By spacing out members of the sample, you're less likely to get a biased sample. In the Chabot study where they did every 30 class, we said, That's going to prevent you from getting unlucky and over-representing math or under-representing PE. We should, by that spacing out, end up getting kind of the right proportion, which is always a good idea and a beneficial thing when you're trying to get a representative sample. And a lot of the times, an advantage like that does occur with systematic. So usually if you see that somebody used a systematic method, you see that as a positive and probably improving how accurate their sample will represent the population. All right, so on to another alternative called cluster sampling. This is a method that chooses items that are somehow already naturally grouped together. Even though we're filling in the word grouped, the word naturally is important too. You're not throwing things into groups. Those groups already exist. And with cluster sampling, you're just making a choice. Instead of choosing individual items, I'm going to choose them as bigger groups and get to my total sample size a little faster. So the process is to identify what the subgroups are. That's what we're going to refer to as our clusters. And those should naturally exist in the data set already. So just as a quick example, going back to that Chabot student satisfaction survey as our example, the people who chose people to come in and do the survey did not actually choose people. They chose classes and then gave the survey to the whole class. So they didn't choose individual students. They chose individual classes, and those would be the clusters in that example. They didn't put the people in those classes. The people picked their own classes. So those groups are already naturally existing in the data. And then you randomly choose a sample of clusters, which is what they did in that study. They chose a certain number of classes to get a sample size that they needed. And then you use all the members of the selected clusters as your sample. So in Chabot's student survey, the clusters were the classes. So there was definitely cluster sampling going on in that Chabot student satisfaction survey. But also in the Chabot study, we could say that it was systematic because the courses were chosen equally spaced in the schedule of classes, and anytime you have that equal spacing going on, there was some systematic part to that process. Could have been just like we described or some other way of spacing them out, but if you're doing equal spacing, you have a systematic sample. Okay, so talking about the cluster sampling, that actually is not usually a good thing to see that. It causes a disadvantage. Clusters usually have like members in them, thus increasing the chance of getting a biased sample. And so if you think about that, the class that you're in right now was not randomly assembled. If it's a class during the day, it tends to have younger students than if it was a class during the evening. And we want that mixture of people, but it's just important to realize that when you choose a cluster, you're more likely to choose 2 night classes and get an overrepresentation of older students than to have that overrepresentation if you just chose students one at a time. Because whenever you choose something, you choose a whole cluster of it at once, and that can cause problems depending on your luck. Essentially, cluster sampling is kind of like having a smaller sample because you're making less random choices. So if I want 600 students and I choose 600 students individually, I'm making 600 random choices. And the more random choices that you make, the less random variation ends up in your results and the more representative your sample gets. So here we may still get to those 600 students, but we might do it choosing only 12 classes. And that smaller amount of random choices creates more random variation in our data. And when there's more random variation, you tend to have larger amounts of sampling error. So we get a bit of a disadvantage from cluster sampling. If for some reason we have to choose in clusters, we should probably go with a bigger sample size than we would normally have chosen to try and end up making more random choices in our clusters and squeezing out that random variation a bit. All right, the final alternative is called stratified sampling. And this is a procedure that chooses items from different subpopulations so that they make up the same proportion of the sample as they did in the population. The process is to identify the subpopulations in the population that you want to represent. From each subpopulation, obtain a simple random sample of a size that is proportional to the size of the subpopulation, and then use all the members obtained in step 2 as your sample. I'm going to work out an example for you below, but in a way we already did one earlier on in the notes when we talked about trying to represent the gender in a sample of Chabot students properly. And so when we wanted that sample of size 450 to be 57.8% female, we took 57.8% of 450 and figured out our sample size that way. So we were talking about representing gender there, but in a stratified sample, you are picking one characteristic and making sure you represent it properly. So it's going to be a very similar process. In a representative sample, you would hope that every single characteristic has that proper representation. In a stratified sample, you're still hoping for that, but you're making sure it happens for at least one. And that creates an advantage because you're ensuring that at least one important characteristic is properly represented. And you'll see we're still going to make some random choices. So there's kind of the normal chance of luck affecting all the other characteristics, but on this one characteristic, we're going to make sure it happens. So let's go ahead and look at an example to see how that works. Okay, so at Chabot College, 3,332 students are 19 or younger, 4,393 are in their early 20s, 1,859 are in their late 20s, 2,269 are in their 30s, and 3,222 are 40 or older. So how many students should be chosen from each age group if you wanted to obtain a sample of size 250 that is stratified based on age? And I think I didn't mention this up here earlier, but when you stratify, because you have these different age groups, you can also, like if you're studying GPA, you can talk about what the GPA is for the younger students, the older students, kind of middle age group students. And if you just did a random sample, you might not note age at all and only look at GPA. So that sometimes makes it more interesting when you can make those comparisons. So anyways, let's get at how that's done. So let's start with the group of 19 or younger. So I'll just put 19 and down. And we want to figure out how many students would we pick in that group. So they want a sample size of 250. So I want to take 250 times the percentage of students that are in that age group in decimal form. So they told us what that was before, and we just took that percentage, 57.8, slid the decimal over to 0.578, and did our multiplication. This time the percentages aren't given, so we have to calculate them ourselves. We know there's 3,332 students that are in that category. So what we want to do is take that and divide that by the total number of students, and that would give us the decimal, which we could then multiply with 250 to get our answer. So unfortunately, they didn't tell us how many students there are total here, so we would just add that up real quick. So bringing in the calculator and clear out that random stuff. And adding those up, we find out there's 15,075 students at Chabot at that time. We'll see this officially later, but our population size is usually written using a capital N, so I'll say that capital N is 15,075. Now if I make that the denominator right here, then doing that division is the same as calculating the decimal form of the percentage. So let me just show you that piece real quick. So the 3332 divided by 15075 is 0.2210281924. We'd usually say that's about 0.221 or 22.1%. But as soon as I shorten that, I'm rounding it and bringing in error. And so after I multiply, we would round again. And it's not good in a process to round more than once because then you bring in error more than once. So the best idea here, instead of going to the decimal, is just taking that 250 and multiplying it immediately by the fraction and going straight to the decimal form of how many students we want in that age group. So it's saying about 55.26. As we discussed earlier, sample size always has to be a whole number. So how many students would we choose from this group? You just go with the nearest whole number, which in this case would be 55, because the 2 we would round down. So that's how many students we want in the 19 and under category, and then we just keep doing that for all the age categories. So in the early 20s, 20 through 24, we still want to do 250, and we still want to multiply by the decimal form of that fraction. So let's see what that would be. Take 4393 for our numerator. The 1505 will stay, and do that calculation. We'll find out how many students we need in the early 20s. You could just type the whole thing in again, but a nice little trick on the calculator. If you hit second and then enter, it'll bring up your last calculation. And since 2 of the 3 numbers stay the same, we can just leave those alone and use the arrow keys to move over our numerator, change it to the new number, and press enter, and we don't have to retype everything. So that's kind of a nice little trick. So that's about 72.85. And if you were to round that to the nearest integer, you would get 73. So now we just need to continue with that process until we get all 5 of those age categories done. So we'll just run through those now. So let's go ahead and write out the next 3. So now we'd have our upper 20s, 25 through 29. So set that up the same way, 250 times, for that group, this is the number, 1859 over 15075. And we'll figure out what that one is in just a moment. Let's go ahead and set up the other ones for the students that are in their 30s. We have 250 times, same idea again, and there's the number for the 30s. So 2269 over 15075. We'll do that one. And then finally for the people who are 40 plus, 250 times, and there's their number, 3222 over 15075. So let's just bring in the calculator and knock all 3 of those out at once. So again, just editing the ones we've already done before. So for this one, I want to change this to 1859 for those students in their upper 20s. So that gives us 30.83 roughly. And rounding that, we would say we should get 31 students from that group. Going to those in their 30s, we would change this number to 2269. So we have about 37.63, which rounding to an integer would be 38. And then going finally to those 40 and above, and changing that to 3 and then 2's. And for that one to get 55.43, which would round to 55. So that's it for every one of those. One final step that you want to take on these would be to add them all up. I just noticed something a little strange, that I have the same answer for both of those, and that shouldn't happen. So I feel like I must have typed this one in wrong or that one in wrong. So let's see. I'm hitting second enter here. You can go back through your old calculations. So what was that one? 55.25. And then, oh, the one I just did I had wrong. Sorry about that. So 53.43. Video proof that I'm not perfect. There's the 53. Okay, so now the final step would be to add all those up. So 55 plus 73 plus 31 plus 38 plus 53 is 250, and that is the size that we were supposed to get. So that all works out perfectly in terms of the sum, and that's kind of what we hope to happen. So there are occasions where it doesn't add up that doesn't total up to what it's supposed to be, in this case the 250 that they asked for. So I'm just going to throw a couple scenarios at you. If this was a 251, that would happen because we rounded up more than we rounded down. And what we would need to do is find one of the ones we rounded up and round it the other way so we get the right total. So just assuming for a moment that happened and I had to pick one of the ones I rounded up and round it down instead, that would come from these 3. And what I would look at is which one was closer to rounding down, which would have been this 37.63. So if my total was too high, I would have picked this one and rounded it down to 37. If the total was too low and I needed to round an extra one up, I would look at the ones I rounded down and say there would be less error in rounding a 4.3 up than rounding a 2.6 up, and I'd make this a 54 instead of a 53. Most times it works out like it did here, where you get the right total. If the total is wrong, though, then we would fix it by picking one and rounding it the opposite way to make the adjustment, and you try and pick the one where rounding it the opposite way creates the smallest amount of rounding error. So hopefully that won't happen to you, but if it does, now you know how to handle it. All right, that wraps up section 1.3.